So Andy, I'd love to start by asking you a little bit more about integrated photonics and what that unlocks that we haven't been able to do before. What are the breakthroughs that come with integrated photonics?
So I'll start by just by saying that I represent Cornerstone, and we're an open access photonics foundry based at the University of Southampton. So we supply, we operate on a commercial basis actually. So roughly 50% of our orders come from industry, mostly startups, 50% from academia. So that shows that we're working on the cutting edge, but we're reasonably repeatable, that industry comes back to us. Our customers have designed over 1,000 different chip designs, and we have supplied over 120 companies in 20 plus countries. And I always bring a sample with me. So there's a sample of one of our photonic integrated circuits. We run a multi-project wafer, which means that we're quite cost effective.
Should we pass it around?
So what we're seeing in terms of our customers and where the market is going, I've drawn a little bit of a roadmap here about how we fit in. Certainly a move from microelectronic based systems to microelectronic combined with photonic systems. So we hear about sort of co-packaged optics, bringing the photonics where it solves the problem, working with microelectronics. And this roadmap kind of displays where that happens in terms of the deployment from cloud-based hyperscalers to distributed sensor systems and distributed AI at the edge. In terms of compute, customers starting to look at optical methods of compute. Heterogeneous integration, we'll hear about sort of packaging, bringing photonic chiplets along with microelectronic chiplets to address certain specific challenges. But also some of the things that photonic chips unlock that you can't do conventionally are things like quantum. So quantum in terms of sensing, in terms of encryption, and in terms of computation. So I'll give a couple of examples. So one of the companies we're working with has developed a quantum position navigation timing chip. Now, this is extremely important when we're trying to navigate around the globe. At the moment, we're reliant on our GPS systems, and very recently, Ursula von der Leyen's flight was interrupted. The GPS was interrupted because it's a satellite system. This company is developing position navigation timing that does not rely on GPS. So firstly, it's uncorruptible. Secondly, it works on the ground, which is pretty handy. And thirdly, it works underwater. So if you're having autonomous underwater vehicles, and the previous session on defence was very pertinent to this discussion, how does that autonomous underwater vehicle navigate to where it's going? So that's certainly one of the aspects we're seeing. And another example is on-chip health diagnostics. So the ability to do spectroscopic analysis, you put a drop of blood on the chip, you can do instantaneous blood analysis. Why that's relevant is quite often when somebody gets a dosage of a drug, the clinician does not exactly know what dosage to give, and especially because of the efficacies of different bodies and what have you. So that quite often they'll prescribe a certain dosage of drug, but they don't know if that's been sufficient. And with a child, you don't know how quickly their metabolism is working. So if you can do an instant blood analysis, maybe half an hour after delivering the drug, you can test its efficacy, and you can see if your dosage is correct. So they're just two of the applications that we see this starting to unlock.
Thank you. Valerio, can you step back a little bit and help me understand the advances in materials and optics that are feeding into integrated photonics and making these other advances we've been talking about possible?
Yeah, I think people would agree, with me that without materials, we wouldn't have components, we wouldn't have systems and eventually applications, right? And actually, it was mentioned that, I guess, that before, if I understood correctly, that 85% of microelectronics, right, is based on silicon. In photonics, silicon is a baseline, but then we have to add other materials, right? Because silicon cannot provide, for example, lasing. And also certain types of modulation and certain types of detection at different wavelengths. And going back to the power of photonics is exactly that you can multiplex. So sometimes you need to work with different wavelengths and put signals on those wavelengths. So we have a wide range, and actually was mentioned PIX Europe. PIX Europe is the photonic integration pilot line of the CHIPS joint undertaking. And there we look at basically all monolithic and also hybridly integrated material platforms. And we have material platforms which are good for, let's say, low loss, so energy efficient devices essentially, and those are, for example, glass or silicon nitride, right? The glass is used for optical fibers, so there wouldn't be internet without optical fibers and glass, thanks for the wide transparency range and low loss. Silicon nitride is also a very interesting material that offers advantages in terms of integration with respect to glass because it has a high index, right? So you can make the circuits smaller. And then we have to add, active materials like 3/5s to make the lasers. But in fact, there is no photonics without electronics, right? Philippe say that, you always need an electronic integrated circuit to drive a photonic integrated circuit. So we will have to have also chips of 3/5s to drive those 3/5 that eventually lays. And then we are studying new materials for modulation, for encoding the signals, right? And these include thin film crystals like lithium niobate and barium titanate that have a very high electro-optic coefficient. That means that if you drive them electrically, you can keep the driving voltages and the energy requirements, right, low. And of course, we also look at more, let's say, advanced material like graphene, for example, is one of them, right? And graphene is a textbook material, I would say, right? And now people are moving a little bit from the thinking that graphene is the material for everything, and they're trying to narrow down and find the killer applications for graphene, right? It's an interesting material because you can really dope it in a control way and change its properties, right? And you can make modulators out of it, which are very fast, actually, and energy efficient. And you can also make detectors, which also go beyond, the standard detector that, for example, you use in telecom that are based on 3/5 in gas, right? And we look also at quantum dots and the way to put those quantum dots on these passive, circuits. And quantum dots is really a material that you can engineer because depending on the particle size, you change the operation wavelength. So when you put all those things together, then we have the problem of stacking those materials together. So there are new techniques to make sure that you can transfer those materials, you can grow those materials, and in many occasions, when you do that, you change the properties, right? Because you have interfaces and so forth.
So is that your biggest, when it comes to integrating into at scale in industry, is that your biggest challenge? I mean, maybe you could all tackle that question.
I think, yeah, the hybrid
the
integration of materials is one challenge. And then you
Right.
have the challenge also, Philippe shown, of co-package optics, for example,
Right.
that then in that case, you integrate more at package level, right? So these are two different and complementary approaches to put the functionalities together, right? So either you do that at chip level, and then you combine those materials and you stack them on
to
one
stack
or the
them and
other.
package
Yeah.
them. Andy, you're busy writing notes, but
I'm thinking about, and I totally agree. I think generally the outside world tends to have an electronic interface. So photonics solves some specific challenges. It solves challenges like high-speed data communication, because as we heard earlier, light has more dimensions than electrical signals. So we have polarization and we have the wavelength, the color of light. And by exploiting those multi-dimensions, we can get more data down the same pipe. But ultimately, the rest of the world tends to be an electronic world. So we've grown up with an electronic world. So we need an interface between the electronics and the photonics. And that electro-optic interface is generally the that's the critical bit for innovation. It's the bit which quite often is the lossy bit. So you want to minimize the number of electro to optical conversions and opto to electrical conversions. And just building on the point about, we can build waveguides in these materials very straightforwardly. So it uses lithography tools which are not cutting edge. So the wavelength of light is typically 400 nanometers, and that means that you need a channel of around about that sort of dimension. So you don't need to go down to 5 nanometers. We can do things at bigger, we need bigger sizes to get the wavelength of light along. So the lithography is not quite so critical, but it doesn't have the active components. It doesn't generate the light, and sometimes it doesn't detect the light. So the biggest challenge then is to develop the emitters, like a laser, and the detectors, and to be able to place them onto the wafer. And that is the innovation challenge.
Thank you.
So
Goedje.
You know, I find it fascinating, right? You know, I worked on photonics. Yeah?
No.
The moment of photonics is happening at the moment. Now I have a challenging question for the three of you. I think you all, you really have a reputation in the way that Europe has been developing the photonics research. If I now look today, and maybe I'm oversimplifying, it's happening what Philippe says, if you look for the next generation of data centers, more and more of the communication will be taking place by photonics. It has to, because of the power consumption, because of the bandwidth. And if you go back there, one of the materials that Europe is strong is indium phosphide. How do we make sure that now, at the moment that you look forward, there will be more and more transceivers needed, that will double and triple in the next few years. And there is not enough indium phosphide capacity in the world in order to make the DFBs, the lasers, in order to make the transceivers for all those AI centers. There's an enormous amount of money. How do we make sure as Europe that we now actually put the foundation of, for instance, laser capacity in Europe to the extent that's needed for the industry, and that we don't fall back into the situation that actually we go on to the next research topic, and actually the business then moves, including the manufacturing capabilities, to either Asia or to the United States. I think if you speak about Europe, this is this Cisco moment for Europe, because actually I compare it at the moment that, let's say, the whole internet started, the whole introduction of all the communication systems, also the fibers, Cisco built up to a massive company. I think we are at this phase with photonics in Europe. We have some of the key research, but if we don't go now to the industrialization and scale up, then actually we'll face the risk of missing the Cisco moment. So I'd like to hear your perspective, what we do differently this time in order to have the Cisco moment and make this a key industry to Europe, and not move to the next research topic.
So let's answer this question. I'm afraid it's probably the last question for this session, but Valerio, go ahead.
Yeah, I can maybe comment on this, right? Indium phosphide, my understanding, I'm not an expert in semiconductor growth, right? But it's a difficult beast, right, to some extent. And already making a 6-inch, indium phosphide wafers for photonics is a challenge, right? So there is a company in the US that I don't name that is offering indium phosphide on a 6-inch scale. There is an action ongoing in the Netherlands, right, to potentiate the indium phosphide production. Actually, in the INPIX Europe, we have as a partner TNO, that is a technology center in the Netherlands that is building actually a fab to produce indium phosphide. And also, I think was mentioned yesterday, Fran, when you presented Spark, right? Spark is looking also at 3.5s, right? Is mainly for electronics, I guess, but then this combination that I mentioned before of electronics and photonics, and maybe, yes, we have a chance there to excel in such material.
Andy.
The UK has a commercial fab that has an indium phosphide capability, and it used to manufacture all the indium phosphide transceivers for subsea communications, and it had a very big contract with a certain mobile phone designer, and when that contract disappeared, the viability of the process kind of ebbed away, but it still has the capability. So now it doesn't do it on 6-inch. I'm pretty sure it's either I think it's a 4-inch. So
it's 4 maybe.
Yeah, so in the UK, but certainly there was a capability, and they're looking for the next opportunity to kind of build on that. So perhaps that's something we could take forward.
I'm going to let Philippe take the last word.
Yeah, I would like to make maybe a controversial comment.
Oh, good.
I think in Europe we had in 3.5, what I see are initiatives to make, or to attempt to make pure play foundries. What I've been confronted with in this type of discussion for 3, and that is very specific to 3.5, I think, is then who is taking the ownership of qualifying the device? And that came up then being the design partner that would qualify it. But in 3.5, the process is so critical. It's very difficult to disentangle the design and the process and this qualification. And I think the biggest, the successful 3.5 companies are actually fully integrated. They make devices. They don't offer foundry services as far as I know. So that's maybe something we need to rethink about 3.5 is, do we want to make foundries or do we want to make IDMs?
First of all, I agree with your statement. You know, it's not clear whether it will be a foundry or IDM. So I think the application knowledge and the technology knowledge is very important. But I want to re-emphasize is, you know, what's going to happen in the world in the next few years, there will be a shortage of lasers based on indium phosphide. Yeah. And either Europe is now going to lean in, not through universities, not through TNO, but in another way in order to create the capacity to deliver that to the rest of the world. Or the rest of the world will build its capacity and will be gone. And I think it's a unique opportunity to actually build a part of the foundation back for photonics industry and based on that build more. That's my very clear view on the situation. So I think the challenge is not the capital. The capital will be there. It's, do we have the guts to really put all the effort into digitalize the technology and go through the whole lab to fab journey, not in 2 or 3 years, but actually in a very short time, because that's what's needed in order to supply the parts to the AI that's needed in all the data centers and other parts. So I think it will be an interesting couple of years, to my opinion, but a unique opportunity.
Yes, actually, I would extend, by the way, there is also a company in Switzerland called Coherent that is making 3.5s, right? But, you know, I would extend your comment on 3.5 also to other materials that are used for photonics, right? This concept, for example, the pilot line, the pilot lines are conceived, you know, to accelerate the product development and demonstrate scalability. We don't actually do scaling. So then we are supposed to transfer for scaling, right? For volume manufacture, as you are saying, right? So, and that is the concept. And then this issue of not having the manufacturers, I think is a quite, you know, a broad issue that is not specific only to indium phosphide, right? You know, it concerns maybe other material platforms too, right? To some extent.
Thank you, all three. I'm afraid we have to break, but there's going to be lots more time for conversation later on. So thank you very much.